Okay, so now we're going to be talking about using nitrogen nucleophiles with reaction with aldehydes and ketones. So specifically, we're going to be first looking at using a primary amine with an aldehyde or ketone to form what's called an imine. The reaction requires acidic conditions to work, and one of the products is water. So if we have a method to remove water during the reaction, that would drive the equilibrium forward, because this is a reversible reaction. We talked about the fact that it needs acidic conditions to work. So this is a pH profile for the reaction. Notice that the optimal reaction rate occurs sort of around a pH of about 4 to 5. So any more acidic than that, meaning a lower pH, the rate actually goes down, because all of the primary amine would be protonated if it was very, very acidic. And there would be no nucleophile left to proceed with the reaction. And if the pH is too high, meaning it's not acidic enough, then there's not enough acid around to catalyze the reaction. So we do need acidic conditions, but we have to be careful with the pH for this particular reaction. Okay, let's analyze the first step in some detail, because it's going to be different than the first step when we had an oxygen nucleophile. So what do I mean by that? So if you recall, when you had an aldehyde or ketone in the past, and we used an oxygen nucleophile, let's say ethanol, for example, that also required acidic conditions, and we also lost water. So water was one of the products. So sort of a very analogous situation. The only difference is the nucleophile, right? So same acidic conditions, and now instead of an alcohol, we would have a primary amine, and we would still lose water. Okay, so there is a difference in the mechanism, because if we analyze the proton transfer situation, we'll see why. So if we're under acidic conditions, the first thing that's going to be protonated is whatever's the most basic thing in solution. So in the case of water and an alcohol, right, the proton transfer would occur on the alcohol, sort of like it would occur on water. So the initial proton transfer would occur between the alcohol and whatever strong acid you used, such as HCl. A similar sort of reaction occurs with amines, because definitely the amine is the best nucleophile in solution, much better than the ketone. So we would get a protonated amine. So this time we wanted 3 hydrogens attached and a positive charge. Okay, so both of these exist in solution, but their pKa's are very different. And that's the crucial part of this. The pKa of a protonated alcohol is going to be sort of similar to hydronium ion. And the pKa of hydronium ion is about -2, right? So we'll say this is approximately -2. But the pKa of ammonium ions is not as acidic, and it's kind of closer to a pKa of 10. So that's very different. The protonated alcohol is much more acidic. So then if we look at the proton transfer reaction between the ketone as the base and the new acid in solution, which is this guy, and we analyze the pKa difference, it's going to be very different. So sort of simultaneously we'll analyze proton transfer from either the protonated alcohol or the ammonium ion. So the products of that proton transfer would be the protonated ketone and also ethanol in this case, or again the same protonated ketone and the primary amine. Okay, so the pKa of the protonated ketone, it's pretty acidic. It's actually about -7. So this being the same thing, we'll write it again down here, -7. So now we're comparing really an acid on one side of -2 versus -7, and then 10 versus -7. So when we think about the difference here, right, to go, neither reaction favors the products because the protonated ketone is the strongest acid in both cases. But here there's a difference of only 10 to the 5 in the first case. And then the difference here would be 10 to the 17. So in the second case, there's 10 to the 17 more reactants, right? Because the equilibrium definitely favors the reverse reaction than products. So there's essentially no products in that reaction. Whereas with the difference of only 10 to the 5, even though the equilibrium still favors the reactants, not by too much that we can't see any product formation. So when we use an alcohol nucleophile, typically we show the first step is proton transfer to the carbonyl carbon of the aldehyde or ketone, because again, there's a smaller pKa difference, so it's more reasonable. But with the second step, when we have a nitrogen nucleophile, we're not actually going to show proton transfer to form the products in this case. So kind of draw a big box around these. These don't form to any appreciable extent because again, the equilibrium lies so far to the left that they don't form. So we're not actually going to show this is the first step in this mechanism. So let's go ahead and draw out what the first step of the mechanism would actually look like. So let's just use a generic ketone. And we're going to be using a primary amine, so we could just use ethylamine, just like we did in the last case. Remember, we did show that some of the primary amine would be protonated. So there will be some ammonium ion in solution. But we carefully didn't add too much acid such that all of the primary amine is converted to ammonium ion. Only some of it is. And we need to make sure that there's still some primary amine in solution, because that's actually going to be involved in our first step. So some free primary amine that hasn't been protonated can do a nucleophilic attack along with this resonance arrow. And again, we're not going to protonate the carbonyl oxygen first, because we said that that was very unlikely based on our pKa analysis. So let's see what that would look like. So initially we would get this intermediate with two charges. So we have a negatively charged oxygen and a positively charged nitrogen. Now again, this is sort of an exception, right? I'm going to go ahead and even write up here, exception. Normally we do not form negatively charged strong base intermediates under acidic conditions, because that's unlikely to form. But in this case, it is likely to form because we're not likely to have protonated that first. And instead, the ammonium ion that's there will rapidly protonate that negatively charged oxygen as soon as it's formed. So we can go ahead and draw. They're definitely under acidic conditions. There is some, I'm going to go ahead and erase that. Okay, we'll try that again. So there definitely is some protonated primary amine because we are under acidic conditions. So that's in solution. And this proton transfer will be very, very rapid because this is a strong base formed under acidic conditions. So that rarely happens. When it does, it would definitely occur. The proton transfer would occur very quickly. Okay, so now we're at a positively charged intermediate, which is much more likely under acidic conditions. So now we're going to need to convert the hydroxyl group into water so that it can leave as water. But we can't protonate it right now because we already have a positively charged intermediate. And forming an intermediate with two positive charges is less stable, so it's not very likely. So what we're going to do is show the proton transfer to remove one of the protons on the nitrogen first, and then we can add a proton on the oxygen after that to avoid forming that intermediate with two positive charges. So we are in a solution of amine, so it's very likely that that will be the base to come in and take this proton. And it might be tempting to try to draw a lot of stuff going on at once, but remember with mechanisms, it's better to show each step separately. So we'll go ahead and draw the deprotonated intermediate. Now it's neutral, so it can pick up another proton to become positively charged. That proton will likely come from another ammonium ion. So now it's a really good leaving group, and it can definitely leave. So we can show loss of a leaving group. And then instead of forming a positive charge on the carbon, we'll just show a resonance arrow at the same time in order to get to the most stable resonance contributor in one step. So then we just need one final proton transfer to form the imine product. And again, you could show water taking this proton, or there's really a lot of primary amine around, so that's probably more likely, but either one is possible. Okay, so this is the imine product. And you notice it because of that carbon nitrogen double bond,